Hello, everyone. I would like to thank the organizers for giving us the opportunity to give this talk. This will be divided in two parts. The first one will given by me, and the second by Héctor. And this is based on these two papers. The main results are on this paper, but we will also explain things based on this previous paper from last year. So the Swampland program aim is to try to determine what are the properties of the effective field theories that can be consistently coupled to gravity. Of course, string theory, since it is a consistent quantum theory of gravity, should satisfy any conjecture property. But there is a stronger statement one can make, which is that all the consistent quantum gravity theories have an theory and string theory description. This is the string Lampos principle. And when there is a high number of space-time dimensions and 16 supercharges, this problem is particularly testable, and it has been there has been a lot of progress last year in these two papers. But the thing is, do we know the landscape in string theory, even with 16 supercharges? The answer is that we only know about it when the dimension is higher or equal to 7. And even in d equals 7, we believe that the picture was complete only with this recent paper by Miguel and Héctor, where they found extra mole spaces for a total of 13. But in 6 dimensions, we have obviously the 13 compactifications of the d equals 7 mole spaces, but there are only 4 known extra mole spaces. And there is not a systematic way of obtaining them. So first, I will give you some constructions for these mole spaces in d equals 7. It's very practical because they all admit an F theory description on different backgrounds. This family here is a theory compactified on a K3, which is elliptically fibered times a circle. And we are applying an orbifold with a shift of order n on the circle. But the constraint is that this orbifold has to preserve the 16 supercharges, because on all this talk, we will always maintain the number of supercharges in 16. Sorry, we will maintain n equal 1, 1 supersymmetry, depends on the dimension. But well, we have 6 possibilities here. The first one is the trivial case. And then we can also do a similar description, changing the K3 with the T4. And we have these 4 theories here. So we have 4 extra mole spaces in 7 dimensions. And then by applying a discrete theta angle, 3 of these can also have an alternative description, but a different mole space, which is a similar description, but with this subtlety. And this was developed by Miguel and Héctor. But the thing is that in 6 dimensions, we have the same mole spaces compactified on a circle, but also there are 2 extra ones here because there is a different description, which is using M theory on K3 times S1. And since on M theory, the K3 is not elliptically fibered, we can also put orbifolds of Z7 and Z8. So we have 2 extra here. These were developed in this paper by De Boer et al. 20 years ago. And also there are 2 more known constructions, which are heterotic on T4 on a non-cyclic orbifold with symmetry Z2 times Z2. And also the Iceland of double Harvey, which is a type 2A on a T4 orbifolded by Z5. So each one of these theories has a rank of the gauge symmetries that characterizes them. For example, this 19 here is the rank of the mole space, which is of the Narain, which is the standard mole space. It is always the biggest one, and all the rest of the theories with 2, 3, 4, 5, 6, or these ones have lower ranks for the gauge symmetries. So we refer to these ones as the mole spaces with rank reduction, and this is the mole space of Narain. We see that in d equals 6, we have bigger ranks. This is because to go from these theories to these ones, usually one adds a circle and this has a cartan, so it makes sense that the rank is higher. It's interesting that this theory here has rank 0. We will talk about this later. It's interesting because this means that it has no moduli. The only degree of freedom is the dilaton.
Sorry, Bernardo, can I ask a quick question about this theory?
Yes.
Yeah, the C5 here, does it have any fixed points?
The C5 here.
The C5, the T4 mod Z5, does the C5 have any fixed points?
I think it has. I mean, the Molly space is just a point.
No, I mean this in space.
You mean on the T4?
The space-time action on the T4.
No,
yes.
I don't know. Sorry.
It's an asymmetric orbifold, Miguel.
Yeah, but does it have so it's not acting geometrically?
Exactly. Yeah.
Yeah, no, it's not geometric, of course.
Okay, thanks.
Sorry. Okay, then the main idea that helped make this works is that all the Mollis spaces for any dimension in principle, but let's focus on the one that we already know, which is in 7, 8, and 9 dimensions, are connected to an array Molly space through a map. This map, we say that is a rank reduction map because it's relating some gauge group in the array component that has rank 17, for example, in 9 space and dimensions, to different Molly spaces with rank reduced groups. So we can say that this map acts on the gauge groups. For example, you have a gauge group here on Arine, and we get a gauge group on CHL or a gauge group on M on Klein Bottle, etc. This was developed on these recent papers. And to get these maps, there are different ways. One is to use lattice embedding techniques involving the Arine lattice and the weight lattice associated to the gauge groups on the specific theories. And it's very nice because in principle, this can be extended to any dimension. So the main goal of this talk is to determine the map in D equals 6. This was done mostly on this paper. But then with this map, we can, for example, check if all the known cases are well understood. I mean, we can use this map to check if all the model spaces give what they need to give. But what we will do is to generalize this map and to apply it to predict new moduli spaces and to make a, in principle, complete classification of them. This was what we did in this paper. So let me give you the main features of this construction. First of all, it predicts 30 new moduli spaces for a total of 47. Since we had 17 and now we have 47. We don't have the construction for all of them, but in principle they are there. We have the gauge symmetries. We also predicts naturally theories with discrete theta angles, including the ones formulated by Miguel and Héctor. It also suggests that pure supergravity has 16 inequivalent ultraviolet completions. This means that there should be 15 constructions analogous to that by Double-Car and Harvey, but they will give a inequivalent theory. So this is very, very nice. And it also, there's a connection with the classification of current algebras in two-dimensional conformal field theories that appear in the worksheet. And also the one novel feature is that some of the small spaces have rank reduction by odd numbers, 15, 17, and 19. This is something new because all the theories known for 6 dimension and all the supercharges, there's always an even rank reduction. So this is very promising.
Sorry, Bernardo, can I ask about that?
Yes.
So
Okay.
Are you saying that the new theories that you find before the theories that you found with this map, were there any examples of theories in 6 dimensions with rank reduction 15, 17, or 19? Or
no, I'm saying that they are all new. The known examples are always even rank.
Good, very good. So you can find odd rank reduction like
Yes,
this.
exactly.
Good. And how many theories have ranks 1? How many theories have rank 1 here?
Rank 1, it's only 1, I think.
Sorry, rank 0. You said 16.
I don't know how you are counting the rank. You mean 1 gauge groups of maximal rank 1.
Sorry. So the ones that you're calling rank 0, there's 16. That's what you're saying there.
Yes.
And all the new examples are related to c equals 12 or c equals 24.
We don't know.
Okay.
Actually, they are.
I will explain
No,
this.
actually, they are not
Parra.
any of them. Yeah, but...
One is 24 and all the others are 12.
Okay, thank you.
Okay. Well, okay, sorry. Well, this talk will be divided in 2 parts, as I told you before. I will give the first part. I will give you a review of lattices and gauge groups, focusing on the Narain lattice, just to help understand what's next. Then I will give a brief explanation of how the rank reduction map works for 7, 8, and 9 dimensions. And when I say dimensions, I'm talking about the space-time dimensions. So 7 dimensions is compactification on ET3, 8 dimension on ET2, and so on. Well, then Héctor will give the generalization that we made of this map to D equals 6 and the classification of Mowgli spaces that we found. And after that, he will explain how we can find all the symmetry enhancements for all these Mowgli spaces. Well, let's start with lattices and gauge groups. The simplest Mowgli space is the Narain Mowgli space. And we see that it appears when one compactifies heterotic strings on a torus. Heterotic strings naturally have 16 supercharges when they are in 10 space-time dimensions. When one compactifies, one does not break any of the supercharges, so we still have theories with full supersymmetry. And the idea is that this gives rise to a Narain Mowgli space. The Narain Mowgli space can be described like this. This is a standard notation. Here we have a quotient of orthogonal groups, which gives the local structure of the space. And then here we have a quotient by the automorphism group of some lattice, which is even and self-dual, and this gives the global structure of the space. This lattice here is called the Narain lattice. It's defined for each D. All of them are the Narain lattices collectively. Well, this Mowgli space, the parameters that describe it are called the moduli, and they are the internal components of the metric, the B field, and Wilson line, and they specify the details of each compactification. And the Narain lattice also encodes the winding number, the momenta, and the charges with respect to the gauge lattice. The gauge lattice is E88 or SO32, depending on which heterotic string we are looking at. For a generic point in the Mowgli space, this is a generic vacuum, we have that the gauge group is abelian. We are ignoring the graviphotons everywhere. So we have an U1 to the D plus 16. And when we move from it here, from a generic point to a boundary of the Mowgli space, we have an enhancement of the symmetry to a non-abelian gauge group. This is not the fundamental region. There's a lot of redundancy here, but this is a slice of the covering space of it. And we see that on all these curves, there are different gauge symmetries, non-abelian gauge symmetries. This is just to have a picture in the mind. But it's interesting that if we take different fundamental regions, in some of them, these curves will be the boundaries. So the picture makes sense. And but this picture is for compactification on a circle. This is D equal 9. And in D equal 9, there's some peculiarity, which is that the full data of everything is encoded in the extending linking diagram. This was noted by Cachaso and Baffo on this paper. And it's there's a very simple method to see what are the possible gauge groups. We just need to remove 2 nodes from this diagram. For example, we take these 2, and we see what are the linking diagram that's left. In this case, it's E8, SU2, E8. But for example, if we take these two, we get SU18. And to get the topology of the group, it's necessary to perform some other specific method. I will not lose time with that. But in this case, for example, topology is not trivial as we have fundamental group Z3. And in this way, we can get everything on D equal 9 on the Narain moduli space. But if we have more dimensions, there is no extended linking diagram. So we are, but we have a different approach, which is that all the possible gauge groups are the ones that have a corresponding Euclidean sublattice that is a sublattice of the Narain lattice. So if we have a W, which corresponds to the weight lattice of some group G, which is embedded in the Narain lattice that corresponds to that compactification, then we will have that gauge group as a symmetry on the moduli space. The root sublattice of W, which is the vectors of length 2, give the massless gauge bosons, and the information about the topology of the gauge group is given by the vectors which are not roots on W. Well, this is an example for 9 dimensions. We see that the weight lattice of spin 32 mod Z2 and of SU18 mod Z3 and of spin 34 are all embedded on the Narain lattice of the circle, which is gamma 17.1. And this means that these 3 groups are all on the moduli space, and we can check that by using the extended linking diagram. For generic D, the classification is very difficult because everything gets more complicated. We have more possibilities and there is no extended linking diagram. But using an exploration algorithm, we have been able to address this for D equal 2 and 3 on these 2 papers. Well, there's also an alternative method using string junctions in D equal 2 in the context of type 2B done on this other paper. Well, we are here focusing on D equal 6. So for D equal 6, things get more complicated, but at the same time, there is a very strong result we got by using theorems of this paper. This sounds a bit incredible, but it's possible to prove that for saying that a W, a weight lattice, is embedded in the Narain lattice of gamma 24, this is for T4 compactifications. This is if only if that same W is embedded in some Niemeyer lattices. Niemeyer lattices are the even and self-dual Euclidean lattices of rank 24, and they were classified long ago. There are only 23 of them with roots. So what this means is that if we take some Niemeyer lattice and we find some W that is inside that lattice, then we already know that that W corresponds to a gauge group on the moduli space of heterotic on T4. Here are some examples of the linking diagrams of the root sublattices of Niemeyer lattices. For example, this one is 3E8, 64. This is always of rank 24.
Sorry, Bernardo, let me.
Yes.
So the point here is that looking for embeddings into an Euclidean lattice is way easier than looking for embeddings into a Lorentzian lattice. Is that right? Is that the?
Yes, exactly.
Okay.
Yes, actually, here is an example of that. If we take some Niemeyer lattice and we delete 4 or more nodes of the linking diagram, we automatically have the diagram of some gauge group on the Narain component. And by doing this with all the 23 Niemeyer lattices, this can be done very quickly because it's something diagrammatically, let's say. So we can get all the results we got from the algorithmic exploration on this paper. This is highly non-trivial because there are 2,252 gauge groups. So I mean, it's very strange that they all match by doing just this very easy computation. But it makes sense because this theorem proves that. So, okay, in this case, for 3E8, we write here the linking diagram. And for example, we remove these 4 nodes, which are in gray. And we see that the algebra gets broken to 2E8 plus 4SU2. And this group is indeed present. We can also do like something like this, remove these ones, and we got an SO10 or like this. But important thing here is that we can remove any choice because all of them will give a W which is embedded in the Niemeyer lattice.
Sorry, Bernardo.
Yes.
I can also take just the 3 E8s, right? Is that also possible?
Yes, and you will get a abelian gauge group.
Sorry, I'm saying like, so you delete nodes, for instance, if you delete a few nodes in the first line, you get 2 E8s because you still have 2 E8s. Is it possible just to take the 3 E8s and therefore have like an E8 gauge symmetry in 6 dimensions in the Narain component?
Yes. Yes. I mean, yeah, I mean, if you remove just 4, you will have a maximal symmetry, but if you remove more, you will have all the.
I'm just not familiar with this point from circumplifications. But okay.
I mean, we need to delete at least 4 nodes. If we remove 3, we get something of rank 21, which is not on the mole space.
I see. Okay.
But if we remove more, we have other groups. The thing is, by looking at the maximal enhancement, we are already describing everything because all the non-maximal enhancement can be obtained by removing nodes from those maximal enhancements. Is okay?
Yeah, no, of course, got it. Sorry, it's just that I forgot that you need to delete at least as many nodes to get their ranks. Okay, thank you.
Yes. Okay. But then the thing is that to get the topology, one needs to compute the exact lattice W. That is like to take the over lattice, but there are different methods of doing this. It is something very technical. That's why I'm not focusing on this here, but it can be done. It's relatively simple, although it's non-trivial. So here is the list of all the thinking diagrams of the Niemeyer lattices. And I want to stress that by taking all of these and removing 4 or more nodes on each one of them, we get all the gauge algebras of 6-dimensional n equal 1, 1 Narain mole space. So we can even say that since all of these diagrams are in the Wikipedia page, wiki/Niemeyer lattice, we could say that all this information is encoded in the Wikipedia, which sounds very bizarre. Okay. This was about the Narain mole space, which seems to be pretty well understood. So let's focus now on the mole spaces with rank reduction. The easiest case is the CHL string. This has a rank reduced by 8 on all the gauge symmetries. And the typical construction, which was done on 95, is to take the Terotti string on a circle and orbifold the theory by a set 2 symmetry that exchange the 2 E8s that define the lattice of the theory, but at the same time make a half shift in S1. This can also be generalized to compactifications on a torus, and we do the half shift on only one of the circles. And at the end of the day, we get a rank reduced theory, which has this moduli space. This is pretty similar to the Narain case, but now we have D+8 instead of D+16 because of the rank reduction. And we also have a quotient by an automorphic group of some lattice, but this lattice, which was constructed by Mikhailov in 98, is even, but it's not self-dual. And the fact that it's not self-dual will change the rules of the game, and we will see that there will appear some subtleties. Well, we call this lattice gamma CHL, and one novel feature is that we will have non-ADE gauge groups. Non-ADE groups are, for example, SPN, the symplectic group, and the spin 2n+1 with something got here, and the exceptional group F4. The thing is that the group data is still encoded in the Euclidean sublattice W or inside the charge lattice gamma CHL. But to get the topology, we need to apply different rules, and this was developed on these papers very recently. But the important thing here, maybe it's the most important thing on all this part, is that this lattice gamma CHL is embedded into an Narain lattice. This was noted by Mikhailov. This is very important because the fact that the CHL lattice is embedded in the Narain lattice, the lattice that corresponds to the mole space of Narain. This means that it's possible to construct a map from one mole space to the other. I will explain this on 9 dimensions, which is the simplest case. The lattice of CHL can be written like this: gamma 1, 1, which is a hyperbolic lattice. This is a lattice of signature 1, 1 of determinant -1, plus the E8 lattice. And on the Narain case, this gamma 1, 1 plus E8 plus E8. So the difference is an E8 factor here. Well, obviously this can be embedded in this. It's very easy to see. But what's more interesting is that if we take a W, which is embedded in the gamma CHL, this is a weight lattice, this will correspond to some gauge group. And we add an E8, we will get something which is isomorphic to a W that can be embedded in Narain. So we start with a gauge group in the CHL moduli space, and we end with the gauge group in the Narain moduli space. So this is a map between groups. And we can invert this map to obtain every group in the CHL moduli space from those of Narain, and the Narains were already computed. So we have a map of gauge groups, which is equivalent to mapping the moduli spaces itself. In the equal 8, this is a bit more complicated, but it's still relatively easy. The embedding is non-trivial because when we go down to 8 space-time dimensions, we were in 9, now we are in 8. We need to add this factor here to the charge lattice. And we see that the gamma 1, 1 here is scaled by a factor of 2. The metric is multiplied by 2. And in Narain, there is no scaling. But this is still embedded here. So we can, again, define a map from Narain to CHL. We have a group that has some spin factor, and this will get mapped to a symplectic group of rank n. Well, this can also be understood microscopically using orientifolds, because the O7 minus plus a stack of 8 D7 brains can be traded with O7 plus because it has the same charge and tension. But the thing is, this blue thing here gives a symmetry to gives a symmetry of a spin 16, and this one does not give a symmetry. So if we add n additional D7 brains, we get exactly this map. Well, this is just a different way of seeing this. In D equals 7, the map generalizes in this way. It's a bit more complicated because now we have 2 spin factors, and each one of them gets mapped to a different symplectic factor. But the thing is, there are other possibilities which cannot be described by this orientifold picture I gave you. One of them is this one, where we have 2 E8 factors, and each one of them is getting mapped to exceptional F4 group. And the idea is that a possible generalization of this orbifold thing, of orientifold thing, is to use Frozen singularities. This was developed in this paper by De Boer et al., and there's a very nice explanation by Tachikawa in 2015. The idea is that this map can be, the CHL theory can be described by M theory on a K-free with Frozen singularities. The Frozen singularity in this case is there are 2 of them, and they are of T4 type on the CHL case. But there are other possible Frozen singularities. These are all of them for the 7-dimensional case. And the idea is that generalizing this map, but using different Frozen singularities, we can get all the 12 moduli spaces on this dimension. And some of them gives 2 different possibilities, but I will not lose time with this. So to finish, this is the, sorry, there was a question. Okay.
Yeah, my internet is pretty bad. I can have a question if you can hear me. On the slide, you had a picture, you had a description terminating 07 minus D8 into 07 plus. And here's the description in terms of freezing.
I cannot hear very well.
Understood.
So
okay,
Jake, we can, exactly. It's best if you type, I think, because we can't hear you very well, unfortunately.
I am the new one, sorry. Let me see. But I don't know if it's good that I think I will stay with full screen, because otherwise this gets a bit laggy. So.
I can read the question for you. So Jake is asking whether the freezing transition has been understood dynamically.
I have no idea. I don't know if you want to answer.
Maybe you can go back full screen.
Yes, I'm trying. You can maybe talk.
Yeah, I think that the answer is no, Jake. I think none of these transitions have been understood. Yeah, I don't think there's anything in the literature. These are non supersymmetric, so.
And there was a... Okay, now you can see.
Well, we are seeing it. We see full screen now. I think good.
Now you can see it. No.
Yes.
Yes. Okay. Sorry. Okay. Well, this is my last slide. So the idea is that using all these other maps that can be constructed from the frozen singularities, it is possible to get like the full landscape on D = 7. These are the 13 Mole spaces. This one on the top left corner is the Narai Mole space, which has rank 19. The rank is written in red. And all the other Mole spaces have reduced rank, like I told you before. And the idea is that all these arrows are the different mappings that we have by freezing these different singularities, which are written here. So this is like the full landscape, we believe, of D = 7 with full supersymmetry. And it's interesting that, for example, this can be constructed with heterotic triples, and these ones, well, they have the F-theory descriptions I gave at the beginning, and these 3 ones here are the last ones obtained using discrete theta angles on this work by Miguel and Héctor. So the Mole spaces of all these constructions, it can be written like this, with difference R depending on the rank of the theory. And here we have different gammas. This is related to the T-duality group on each case and gives the global structure. So well, in the remaining of the talk, the idea is to generalize this picture to the D = 6 case. And in doing so, we get a map that characterizes the D = 6 landscape. So I think now it's Héctor's turn. I will try to stop the shading. Okay, perfect.
Thank you, Bernardo. Maybe, yeah, okay. So Héctor, you go. Maybe we hold off like general questions for Bernardo till the end. So Héctor, can you
Héctor, you are mute.
share full screen? You're muted. You're still muted.
Yeah. Okay, now?
Okay.
So should I start?
Yes, please, of course.
Okay.
But you're not full screen. Okay, yeah. Sorry.
Okay, so I would also like to thank the organizers for giving us the opportunity to talk here. And before moving on, I just want to quickly recapitulate what was the content of what Bernardo said. There are 2 main points. The first one is that non-abelian gauge symmetries, non-abelian gauge symmetries can always be encoded in sublattices, the value of the charge lattice of a moduli space when there are 16 supercharges. So these moduli spaces always takes this generic form, where R is the rank of the gauge groups and D is the number of compact dimensions if you are using a 10-dimensional theory. But more generally, it's 10 minus the number of space-time dimensions. And in the case of D = 1, 2, 3, small d = 1, 2, 3, there are maps acting on these gauge symmetries in the Narai moduli space to produce those of all the other moduli spaces. So these maps are well understood. And what we want to do now is look at the 6-dimensional case. So the first thing that I will do is tell you what is the actual map, how it works, and then explain some details about it and how we can actually find it and what are the consequences. Now, in 6 dimensions, this map, the map that we find, it acts on the gauge groups at the level of the, it acts depending on the topology, the gauge groups. So, for example, take this group spin 32 mod set 2. It's very well known. It's the one that you get in 10-dimensional heterotic string, for example, but of course it will also be there in 6 dimensions. And here the map will take that group and map it to spin 17, which is non-simply laced. And you see that the topology will change. This is a general feature of the map. And it gives rank reduction by 8. Now, since it's reducing the rank, in this case, it will map to the CHL string. The other example, another nice example is E6, 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 mod set 3, diagonal set 3. It will map to G2 times G2 times G2. And here the rank is instead reduced by 12. So it will give you another moduli space. It will be your H group in another moduli space. Now, this transformation is determined by the fundamental group. It's determined in particular by an element of the fundamental group in maps to a given moduli space. So then, if you have a classification of all of these fundamental groups that can appear, which you get from the classification of H groups in the Nari moduli space, then in principle, you can have a classification of moduli spaces and see how that looks like. So to understand intuitively how this map works, you can think in terms of thinking diagrams. In the case that I mentioned before, the spin 32, you can draw the affine thinking diagram for spin 32 or SO32, and you see that it has a symmetry, a set 2 symmetry. This symmetry is related to that set 2 that is quotient in the spin 32. And if you follow the diagram, there are certain rules to do this consistently, and you get precisely the affine diagram for spin 17, which is not simply laced. You can see it here. Maybe I can also use a pointer. For the E6, it's a similar situation. Now you have a threefold symmetry in the affine thinking diagram. And when you apply it, you get the affine thinking diagram for 3G2. And this map, it looks very natural. It, in fact, appears in many other contexts. So, for example, it relates the moduli spaces of flat connections on G bundles on the torus, on T2, with G non-simply connected. Of course, G has to be non-simply connected in order to define this map, to have non-trivial fundamental group. And this was shown in a paper of Schweiger in 1997, and that's where I became aware of it. Perhaps more important for us is the fact that it appears in the classification of current algebras for two-dimensional chiral CFTs with central charge 24. You apply this on the Niemeyer lattices, and you will get lattices that are related to this current algebras. And this was worked out in detail by Ho in 17. So it's in the mathematics literature. An interesting fact that we notice in this work is that this construction not only classifies these current algebras for chiral CFTs, bosonic CFTs, but also for superconformal theories with central charge 12. This is relevant, as we will see, to have type 2 descriptions and so on. But the question is, why does it appear here in this 6D landscape? You could think maybe that it should appear in 8 dimensions, because in 8 dimensions, you compactify on tori. And since this map is related to G bundles on tori, on T2, then it should appear there. But in fact, it appears here in 6 dimensions. So, but why? Well, we can understand this. We can prove that it's here in the following way. The first thing is to recall that every charge lattice embeds into the Nari lattice, as Bernardo said. But the details of this embedding will depend on the dimension, the number of space-time dimensions. So, for example, in 9 dimensions, it's very simple to see this embedding, but it changes as you compactify. Now, in the critical value of D equals 6, something very special happens. When you do this embedding for any of the charge lattices that we know, and you take the orthogonal complement, you always find a lattice that is the weight lattice of a group of the following form. It always takes this form. It's a product of SUNs quotiented by some subgroup of the center. And so, to give some simple examples, you can think of the heterotic holonomy triples, which are the constructions that you can do in 7 dimensions, but in this case we are in 6 dimensions, and they take this simple form. The first case in this series is dual to the CHL string, so you have SU2 to the 8 mod set 2. Now, you can maybe associate these objects with singularities in some geometric settings which are relevant for compactifications of theory and so on. And it's interesting to explore that, what is the geometrical meaning of these things, but for us, it will not be that relevant. So another thing to have in mind is that if you have a group in the Rye modular space and you want to map it, and you want to know when you can map it, we said it has to have a non-trivial topology, but in terms of lattices, it has to be such that the weight lattice of that group, it contains as a sublattice this special sublattice lambda, the one that I mentioned here before. And then the mapping of one group to the other at the level of lattices, it roughly consists in taking the orthogonal complement of the lambda. And the very special thing that happens here is that taking the orthogonal complement of a lattice of this form is completely equivalent to folding the Dinkin diagram associated to it. So here, this is a picture similar to the one that we saw before, but we are not folding. We're taking an orthogonal complement of the lattice corresponding to the nodes that are in yellow. And here you have 8 nodes. So this means that this corresponds to the SU2 to the 8. You take the orthogonal complement of the lattice and you end up with a lattice that can be interpreted in this way. So it's equivalent to what we already saw. And since this is SU2 to the 8, we can associate it to the CHL string. So we know that what we get is in the CHL string. In the case of the 3, 6 is a similar picture. Now the nodes in yellow correspond to SU3 to the 6. And when you take the orthogonal complement of the lattice, you recover what you expect, which is the following. Okay, so how can we use this information to classify the moduli space, the different moduli spaces? Well, the thing is that to every sublattice lambda, we can associate elements of fundamental group of some gauge symmetry group, and then associate to it a map to some moduli space. Then if we can classify the gauge groups in the Rye moduli space, we can obtain every possible lambda, because we know the topologies of those groups. And to each one of these lambda associate a moduli space. But how do you get the actual moduli space? So as I mentioned, the lambda is defined by taking the orthogonal complement of a charge lattice inside an array for the charge lattices that we know. So we just invert this procedure and we say, okay, I will embed the lambda that I have into the array lattice and I will take the orthogonal complement. And that will give me the charge lattice of my theory, my moduli space. What do we find? We have 46 inequivalent lambdas. 23 of them correspond to foldings, to doing one folding in Dinkin diagrams, and in turn, this corresponds to cyclic orbitals. And when we construct all the possible charge lattices, we see that 15 of them correspond to the theories that we already know, the cyclic ones. And 8 more are predicted, but we don't know the construction. The next step is to assume that we can apply this map many times, or that we can fold more than one time. And this roughly corresponds to taking compositions of lambdas. So there are lambdas that are well defined this way, and they correspond to more complicated subgroups of fundamental groups, and they correspond to non-cyclic orbitals. We have 23 of them also, and one of them coincides with a theory that has been constructed in the literature. Is one that Bernardo mentioned, that is asymmetric orbifold in the heterotic string of D4. This time quotiented by set 2, set 2. But the other 22 we haven't, we don't know how to construct, and maybe also doing asymmetric orbifolds. Now, out of these 46 theories, there are 16 where the lambda, or out of the 46 lambdas, there are 16 that have rank 20. And the rank of lambda gives you the rank reduction. And since the maximal rank in 6 dimensions is 20, these lambdas reduce all the rank. So they give you rank 0, they are string islands. And of all the 16s, we can identify one of them with the one constructed by double current Harvey, this asymmetric orbifold in type 2A. Okay. Now, here I just...
So, Héctor, sorry, can I ask, yes. What can you tell us about the new 16, like the new 15 string islands that you have found? Can you say anything about its physics, like your massive states are different, or because they correspond to different embeddings, right?
Yes. I will show in a moment a table with the data of those theories and make some comments on it.
Right. This is amazing.
But before that, just to give an overview of what are the results, it may look a bit complicated, but let me explain. There are two tables. The table on the left corresponds to the cyclic orbitals. And here the data is as follows. You have the charge lattice is written here in the first in this column, then the rank of that lattice, and then the orbital group basically. So you see all of these are cyclic. Okay. Then here you have the orthogonal complement of the charge lattice inside the non-line lattice, which is that lambda that I was talking about. Notice that all of them have they are factors. They have factors of a sub n, which correspond to SUN in this notation. This thing here, this genus has to do with the classification is in connection with two-dimensional CFTs, but it's not relevant for now. And here we have the realizations of some of those theories, or some possible realizations, while those that have a question mark, we don't know the construction. In the right side, we have the case, the non-cyclic case. As you can see, there is only one of them for which we have a construction, and for the others we don't. But here is where we can pinpoint those moduli spaces that are predicted to have odd rank reduction. So you have 4 of them. 2 with rank 9 in the lattice. So the lattice is rank 9. It means that the gauge group will have rank 5. So this would be rank 5, 3, and 1. So to answer the question from before, there is one theory that has rank 1, one with rank 3, and one with two with rank 5. One can be tempted to think that these two theories here are related by discrete theta angles. The ones with rank 9, and the reason is because you can usually see this feature of having discrete theta angles in these lattices here. As you can see, they have the same ADA type, but they differ at the level of the extra vectors that complete the lattice. So this is related to S2 to the 4 and S2 to the 3, if you think of it as gauge groups, weight lattices. And this is the same feature that we can see in the theories that we know have discrete theta angles. So it may be the case that it's the same thing here. Now, I want to focus now on the islands, on the 16 theories that have rank 0. So they are collected here in this table. And also to answer a question from before, we can show that these theories, if you compactify them to 2 dimensions, they will have some description, some stringent description in which the left moving central charge in the worldsheet will be 12. In the internal CFT, it will be 12. So they should be described by type 2 theories. This is the case for the one that we know. There is one of them that may have a heterotic description, because for that one, the worldsheet has central charge, left moving central charge equal to 24. So this is 26 for the whole CFT. But the internal will have 24. And here again, we can see that some of them seem to exhibit also this feature of discrete theta angles in some frame. This is the case, for example, with the Davarkar-Harvey string islands. I think this theory should admit a discrete theta angle in some description. You can see again that the ADA type of this lattice is the same, but it differs at the level of it really differs at the level of the topology of the gauge groups. It differs at the level of massive states. And all of these 16 theories are inequivalent. You can see that because the charge lattices are different. Now here, the charge lattices are Euclidean and rank 4. So they are giving you information about the graviphotons. They are giving you information about massive states that couple to the graviphotons, really. And for all of them, they are different. So there should be 16 equivalent unparalleled completions of pure supergravity in 6 dimensions with 60 supercharges. Okay. I hope this answers some questions. Now, having said that, let's talk about gauge symmetries. Not only in the spirit of classifying gauge symmetries, something that we can do, but we can learn things about these theories also. So to start with, recall that every gauge group in the 9 moduli space is encoded in the 9-Meyer lattices by deleting 4 or more nodes. But it turns out that, so when you delete those 4 nodes, you end up with some lattice that you can fold to get a a group in another moduli space. But these two operations of deleting nodes and folding, they commute. You can see that they commute. So you can do it the other way around. You can take the Neumeier lattices, you can fold them, and then this will give you a list of lattices from which you can obtain every possible symmetry enhancement for a given moduli space. Okay. And this is an example for the CHL string. I'm giving two lattices, but now we'll show the complete set. So the game here is the same. You take one of these diagrams, you delete 4 nodes, and you get a group in the CHL string in 6 dimensions. And you can see that you have before and so many non-simply laced groups. This is the full list. There are 17 of them. Okay. It is true that as you reduce more the rank, so the CHL string you reduce by 8, but as you reduce more the rank, you get less of these lattices. And we call these things orbit lattices. It's a name that is used in the literature, so we go by it. What is the physical significance of this? Can we say something meaningful? Well, we can, if we connect this with the classification of CFTs that I talked about previously, that I mentioned. In the case of the cyclic orbifolds, where you fold once the Neumeier lattices, these orbit lattices, they actually realize they realize two-dimensional Kerr CFTs, bosonic with C equal 24. This is the so-called classification of Schellekens back in '92, and this relation between the orbit lattices and the CFTs was done by Hong in 17, as I mentioned. The orbit lattices that correspond to these CFTs, they are in groups, and each one of those groups corresponds to a moduli space, and you have 10 in total of the 23. The other 13, they have orbit lattices, but they do not correspond to these CFTs. They correspond, in fact, to superconformal field theories. They correspond to one, so they correspond to the superconformal field theory based on 24 fermions. It was studied in this paper here. And you can see explicitly that the algebras match the classification. But is there a relation between these things? You have some 6-dimensional thing going on and some 2-dimensional CFTs. What is the actual physical relation? Okay, to see this, we have to note that if you take one of these CFTs and you tensor it with the superconformal field theory based on the E8 lattice, you will produce the internal CFT of a string worldsheet in 2 dimensions, with 2-dimensional target space, with 16 supercharges. And this can be understood at the level of lattices. So to be precise, you take the orbit lattice, that is related to a folding of the Neumeier lattice, and you take the orthogonal sum with the E8 lattice with some scaling. Now, this scaling is just the order of the orbifold. Recall we're in cyclic case. This thing turns out to be isomorphic to a charged lattice. That is the compactification on T4 of the 6-dimensional theory from which the orbit lattices come. So you establish a relation between the 6-dimensional theory, its compactification to 2 dimensions, using all of these orbit lattices and CFTs. And so how can we see this? Here is a drawing. I hope it's helpful. And this is the moduli space for the 2-dimensional theory. You have a 2-dimensional theory that you got, I don't know, doing this tensor of CFTs. A priori it's here. And you have some points of maximal enhancement. Now, at these points, the thing that is special in 2 dimensions is that at these points, the worldsheet CFT, it can factorize. It can become the tensor product of 2 CFTs, and one of them corresponds to an orbit lattice. And here, in principle, if this is the CHL string, for example, you would have 17 such points, each one corresponding to an orbit lattice. Okay. But recall that if you delete 4 nodes of these diagrams, you get the symmetries for the 6-dimensional theory. Okay. So if you do break it, why? Because when you delete a node, it corresponds to moving away from the point of symmetry enhancement. You can think of every node as imposing a constraint in moduli space. When you delete 4 of them, you move 4 times, and this breaks the symmetry. If you do it in all possible ways for all of these points, you get all the list of enhancements in 6 dimensions. It looks something like this. For every moduli space in 6 dimensions, you always have this picture. You have the 2-dimensional version and the 6-dimensional version, and all the symmetries are encoded here. Okay. So, okay. so this is what we learned. The nice thing about this picture is not only physically nice, but it's also useful. In fact, I didn't say this explicitly, but we have been talking about computing gauge symmetries from lattices. This is something that in general we don't know how to do. We know how to do it explicitly in the heterotic constructions, but in something like a type 2 construction, I don't know how to do it. But what we did was use this connection between 6 dimensions and 2 dimensions. We established a relation between those compactifications and these CFTs. And for these CFTs, we know how to compute the gauge symmetries. They are done, they are in the literature. And for those CFTs, you also have the charge lattice. So you can establish a relation between let's say, the current algebra in the CFT with the charge lattice. You establish some rules for computing the symmetries, and then you take those rules and you uplift them to 6 dimensions. You do this, and we see that they match exactly what we found in the heterotic cases, and they also predict very consistently the rules for obtaining the gauge symmetries in the other components, in every component. So in fact, without this, we would not have been able to say that this map actually is there, that it actually is general enough. So this was the missing part that we use in this paper. Now, for non-cyclic orbitals, this picture is the same in the sense that you can still compactify the thing to 2 dimensions. You have these points of factorization, but now the CFTs, they are no longer in the classifications that I have mentioned. They are of a different kind. They don't correspond to so-called self-dual vertex operator algebras, and it will be good to understand this better without these CFTs, but it would be a problem for the future. And yes, so I think I will wrap up. So just to conclude, this is essentially what we mentioned at the beginning. But the message is this: you have 16 components, the moduli space, 16 moduli spaces in 6 dimensions. They are connected by a map based on the group topology. You can use it to predict new moduli spaces in a unified way. Now, all of these moduli spaces, you can understand as being part of one consistent construction. And 16 of them are islands, so they only have the dilaton as a modulus. You can have odd rank reduction. Again, I emphasize this. Would be good to understand. And you can encode all the gauge symmetries in the 6 dimensions, in the 2 dimensions. I could say that this relation between 6 dimensions and 2 dimensions, it has appeared in other contexts related to moonshine, but in a slightly different way. So yes. And now for the future, there are many questions, of course. Here I want to mention the ones that I think are most important. The first is, of course, how would you be able to construct these theories? So perhaps you could use behavior of manifolds. These were useful to construct some predicted theories in 7 dimensions and above in the work that I had with Miguel. And perhaps more interestingly, can you have a universal picture of these constructions that is analogous to the one of Rosen singularities? So because the point of Rosen singularities, for me at least, is it gives you a complete picture of the moduli space. So can we have something here? Maybe using type 2A strings on KG manifolds. Do these theories exhibit novel properties? We saw this with the discrete theta angles. They have incomplete spectra of BPS strings. Here we see that there are other theories which may have discrete angles, but are there theories that exhibit other interesting properties? Can they be used to test some Swampland conjectures? It would be nice to check this. And of course, this is with 16 supercharges. You can ask if there are relations like this among gauge groups in different moduli spaces when you break supersymmetry. I think there are if you break supersymmetry completely, such as in the 10-dimensional heterotic string, but something more subtle like theories with 8 supercharges would be interesting to know. And now I provided an explanation for why the map is here, but it would be nice to have like a physical explanation for it related to these bundles on tori, maybe like some geometric explanation from the compactification itself. And can you predict that this structure will arise using some constraints, perhaps using prime probes, as was done in the recent papers on string universality? Because there is this relation to the CFTs. So yes, that's what I wanted to say. So thank you.